Sometimes question is not which of two options is better. Sometimes real life is messier. You are testing three teaching methods, not two. You are running four marketing campaigns, not one A/B test. You are comparing multiple machine settings, not just old versus new. You are studying different drug doses, not just placebo versus treatment. So, you collect data, you calculate averages, and then comes the big question: which group is actually different? And is that difference real or just random noise? Now, here's the problem. If we compare groups two at a time using t-test like A versus B, A versus C, and B versus C, we increase confusion, error, also risk of false conclusions. So, how do statisticians handle more than two groups without losing reliability? That's where ANOVA comes in. Welcome back to Shital's Data Days. I'm Shital, and in this video, we are going to deeply understand ANOVA step by step with intuition, visuals, and real world examples. In this video, we are going to cover why t-tests are not enough. What is ANOVA? Why ANOVA compares variance, not means. Intuition behind ANOVA. What is F-Statistic? What does ANOVA actually conclude? Types of ANOVA, assumptions, common misconceptions, and when not to use ANOVA. So, let's start with exact problem ANOVA is designed to solve. Imagine this. You are comparing three teaching methods. Average score of method A is 72, method B is 76, and method C is 79. At first glance, method C looks best. But how do you test this statistically? If you use t-test, A versus B, A versus C, and B versus C, that's three tests already. Each test has chance of making false positive error. As number of tests increases, chance of making at least one false conclusion skyrockets. This is called error inflation. Statistics doesn't like guessing. It likes controlled decision making. So, instead of asking which pairs are different, ANOVA asks, is there any real difference among these group averages? So, what exactly is ANOVA? ANOVA stands for Analysis of Variance. At its core, ANOVA is statistical method used to determine whether at least one group mean is significantly different from others. In simple words, ANOVA answers these questions. Are differences we see between group averages real? Or could they have happened just by random chance? Important clarification is ANOVA does not tell us which groups are different. It tells us whether difference exists at all. That might sound surprising, but it is exactly what ANOVA makes powerful and safe. So, ANOVA helps us decide whether difference between group averages are real. But this leads to very natural question. If we care about averages, why is it called analysis of variance? Here's the intuition. ANOVA looks at two types of variation. First, variation between groups. How far apart are group averages? And second, variation within groups. How spread out data inside each group? Think of it like this. If group averages are far apart and each group internally is consistent, then those differences start to look meaningful. But if group averages are close or data inside groups is very noisy, then differences may just be random. So, ANOVA doesn't trust means blindly. It asks, is the difference between groups large relative to natural variation? That's why variance is the star of the show. Let's build intuition with an example. Imagine three cafes measuring customer satisfaction scores. Scenario 1: Cafe A score is tightly clustered around 80. Cafe B score tightly clustered around 85. And Cafe C score tightly clustered around 90. Low variability within each cafe and clear separation between averages. So, ANOVA will likely to say, yes, these differences are real. Scenario 2: Cafe A score is widely spread from 50 to 95. Cafe B scores equally messy as Cafe C score. Even if averages differ slightly, ANOVA will likely to say These differences could be noise. So, ANOVA is really asking, is the signal stronger than noise? So, how does ANOVA turn this intuition into a number? It uses something called F-statistics. F-statistic is simply a ratio, variation between groups divided by variation within groups. In simple terms, large F value means group differences dominate noise, and small f value means noise dominates differences. If F statistics is large enough, we conclude that not all group means are equal. That's it. No magic. Just a comparison of signal to noise. Just like t-test but extended to many groups. So, F statistics tells us whether group differences dominate random variation. But once we compute it, what exactly are we allowed to conclude? This part is crucial. After ANOVA, we do not say group C is best. Instead, we say there is statistically significant evidence that at least one group mean differs from others. ANOVA answers existence questions, not location questions. If ANOVA is significant, we then use post hoc tests like Tukey's test to identify which groups differ. Now that we understand what ANOVA tells us, and just as importantly, what it doesn't, let's look at different forms ANOVA can take depending on situation. ANOVA is not just one test. Let's look at most common types. First, one-way ANOVA. One-way ANOVA is used when you are studying one categorical factor with multiple groups. In other words, there is only one reason why groups are different. For example, you want to see whether teaching method affects test scores. Teaching method is factor and different methods are groups. And ANOVA checks whether average test scores differ across those methods. Second, two-way ANOVA. Two-way ANOVA is used when you have two factors, not just one. This allows us to study two things at the same time and something even more powerful. For example, you want to study how teaching method and class size together affect test scores. Here, ANOVA answers three questions. Does teaching method matter? Does class size matter? And most importantly, does effect of teaching method depend on class size? That last question is called interaction effect, and that's what makes two-way ANOVA so powerful. Third, repeated measures ANOVA. Repeated measures ANOVA is used when same objects are measured multiple times. In other words, each subject acts as their own control. For example, you measure performance before training, during training, and after training. Here, we are not comparing different people or different groups. We are comparing same individuals across time or across different conditions. Repeated measures ANOVA works by focusing on how each subject changes over time rather than differences between people. This makes it very powerful because it removes lot of individual variability. That's why you will often hear it described as ANOVA version of paired t-test, just extended to more than two time points or conditions. So, ANOVA comes in different versions for different experimental setup. But regardless of the type, all ANOVA tests rely on some common set of assumptions. Like all statistical tools, ANOVA has assumptions. First, independence of observations. Second, approximate normality. And third, equal variance across groups. Good news is ANOVA is quite robust, especially with larger samples. But when these assumptions are misunderstood or ignored, they often lead to incorrect interpretations. So, let's clear up some common misconceptions about ANOVA. First, ANOVA tells me which group is best. No, post hoc tests do that. Second, significant ANOVA means large differences. No, it means unlikely due to chance. Third, if ANOVA is not significant, nothing matters. Not necessarily. Power and sample size matter. Once we understand what ANOVA can and cannot tell us, another important question follows. Should we always use ANOVA whenever we have data? Don't use ANOVA when you only have two groups. In that case, use t-test. Data is extremely non-normal with strong outliers. Observations are not independent. Outcome is categorical, not numerical. Statistics is about choosing right tool, not forcing one. So, ANOVA is powerful tool, but only when used in right context. Let's step back and summarize big ideas. ANOVA handles comparisons across multiple groups. It focuses on variance, not just means. F-Statistics compares signal to noise. ANOVA test whether differences exist, not where they exist. Assumptions matter, and statistical significance is not the same as practical importance. At a deeper level, ANOVA is not just about math or formulas. It is about disciplined thinking when comparisons become complex. ANOVA teaches us powerful lesson. When comparisons get complex, structure and discipline matter more than intuition. This is Chital's Data Desk, where we don't fear complexity, we understand it. Thanks for watching, and I'll see you in next video.